why do we study history? Like, what do you guys think? Why do we do history?
Predict the future.
Yeah, like exactly. Like if we do the history, we get a good idea about the present and the future in a much better sense. So in the same way, for understanding climate as a whole, we have to look at the past of the climate. So we get the patterns and we get to predict the future. So in history we see records, right? We need some kind of records to predict, to see the past. So for paleoclimate studies, what are the records that we have? So from 1750 onwards, there were some measurements that was taken by some instruments. And you can see there are some historical written records from 2000 years ago. For example, if you take the rings of a tree, every year new rings are formed. We get the idea of time. Every year a spring wood and autumn wood forms. And we get the idea of time and the material that was formed at that point of time. So this material will be having some kind of signature or some kind of record on the environment at that point of time. So that's the basic idea of paleoclimate. If we see the same way, during my internship, I was mostly focused on the ocean sediments. And if we see ocean sediments are almost going back to 100 billion years. So it's a huge amount of past that we are able to discover using the ocean sediments. So in the ocean sediments, I was mostly focusing on corals and foraminifera, as I said. I will introduce what the foraminifera is basically after some time. So why do we use foraminifera and coral samples? They are abundant in nature. If you just take any ocean sediments, we get to see them everywhere. So and they're sensitive to the environment. Whatever environment changes that happens is being reflected in their chemistry. And they occur at different depths of the sea, and they incorporate different minor elements and trace elements. So foraminifera are basically single cell focus which form a calcium shell around them. Okay. So this shell is also called a test. So this test will be having some kind of minor elements and trace elements. So this is calcium test. So obviously the major elements are calcium, oxygen, carbon, like CaCO3. And the minor elements I have given few examples to just introduce you to this. So as I've already told you, from the past, what are the information that we are able to get? So if we look at, if we analyze the magnesium per calcium ratio, we are able to find the temperature, the past temperature. If we look at the boron, we get to see the pH. In a similar way, if we look at strontium, it is having an inverse relation with temperature. Like why is it so? Because strontium, when it replaces the calcium in the matrix, it is an exothermic reaction, unlike in the case of Mg. So it is having that kind of relationship. And if we see cadmium, it is related to the nutrient phosphate levels, and iron manganese is related to the redox emission. Lithium calcium, this is a evolving, like people are still experimenting in it. It's a new field actually. So it is having a relation to temperature, silicate gathering, and various things. Now, I will. So in this slide, you can see there are two equations. I want to look at them. So see, we can see the magnesium calcium ratio is related to the temperature, and it is having an exponential relation. So we get to find if we take any foraminifera at some point of time, and we measure the magnesium to calcium ratio, and we input in this relation, we get to see the temperature at that time. So we can couple it with this delta 18O values to get more information out of this. So how do we do that? This delta 18OC is the delta 18O value of the carbonate calcite shell of the foraminifera, and this delta 18OW is the seawater delta 18O value. We can't measure the seawater delta 18O value of the past because we don't have the past ocean water. We only have the calcite shell. So if we take the temperature value from this and we put it why is this delta OW very important? Because if you guys recall from Sujata's course or Sanyasa's course, we know this delta 18O of the seawater will give us very information about the salinity, then how the evaporation was, then the ice melting that was happening at that time. So by coupling these two things, we are able to get more things like that. So there is a fractionation of this heavier delta, heavier isotope of oxygen during evaporation. So for the non-science people, I'm just elaborating on that. So because of that, there are many other things. Like it is directly related to the salinity in oceans. When there is more evaporation, there is more salinity, and when there is more ice melting that happens, there is less salinity. Okay, this graph is just showing both this delta 18O and magnesium calcium ratios are having a, like both are showing the temperature is having a linear relation. So how do we get these foraminifera samples? So people have been, scientists have been going for some drilling projects since 1968 till present. So there is DSDP project, ODP, IODP, etc. So these projects, they go and take the samples from the ocean bottom, and they take a core like this. So we get the samples, and every core is divided into different sections, and every section is divided into different sections. And whenever we get a sample in a bottle, it will have a name like this you can see. So from this name we can understand at what depth that sample is being collected. So this is how, if we get the depth, we can get at what age this foraminifera was deposited in the ocean floor. So as I already told you, these projects are having their publications. So if you look at their publications, we get to see the lithostratigraphy, biostratigraphy, paleomagnetism, and a whole lot of information about that sample from their side. So it is a very good tool that we have. Now, if we look at this slide, you can see there are fundamental differences. Can you try to see, like this is a different thing, this is a different thing. Like this is more globular. What do you think about this? This is a kind of more pointy, right? This is pointy, this is like flat. These are having a thicker shell. This is having pores in it. So what is the main fundamental difference is that this is seen in the ocean floor and this is floating around. So these are called plantar foraminifera and genetic foraminifera, and these are the like broad classification of foraminifera. So we pick these foraminifera using a microscope and a wet small brush. We do that. So when we get the sample, it is having everything. It will be having theropods, it will be having like radiolarians, like all kinds of organisms in the seabed. It will be having all. So we only need the foraminifera that specific species we have to pick using the microscope. So these are the samples that are picked in slides. And in this slide, you can see there is Ubizarina. These are Cibiciloides, these are Papilloma, this is Ruber. These are picked through the microscope. And I've written on top geochemical analysis is species specific. What does that mean? So, if we see, compare an elephant and a boar, they eat differently, right? They have different dietary preferences. So, if we take a sample of, like if we do the geochemical analysis using some different set of let's say species, and let's say one lab is taking the data from one set of species and another lab is taking species, a different set of species, and we can't compare these two data because these are two different species. They incorporate those minor trace elements differently. So we have to pick one specific species tell the geochemical analysis. Otherwise, it doesn't have any meaning. So that's why we have to pick one single species. So it's important to identify species. So what are the species we have? For identifying have to have a develop an idea of the taxonomy. So during my internship, a lot of time was spent on identifying species. So this is a website where there is a catalog of a lot of species, like there are thousands of species. So it's very hard if you look at one species in a microscope. It's very hard to say which species it is by going through the catalog because there is a lot of species. So we have to go through a systematic much more easier way. So what we do is we try to understand what are the basic difference between common genuses that are there. So these are the common genuses like Globigenoides, like these, like everything has some small differences. So we look through the microscope and if you look some foraminifera, we should be able to identify which genus it is. If we know the genus, then it will be easier to find the species because our sample space is reduced. So these are some things we can look in a foraminifera, like the coiling direction, the where the chambers are arranged. If it is coiled like going up like tropospiral, or is it a flat planar? We can look at the aperture. It is having an aperture, the shape of the aperture, where the position of the aperture. Aperture can have some other features like lip-like features, then tooth-like features. It can have a cavity for buoyancy, it is called keel. It can have spines on top of it. We can look at the texture of the foraminifera. We can look at the size of the pores. For example, if we look at this species, a fundamental thing that suddenly comes to us is that the pores are very big. The texture of the test is something that we can look. Here you can see how it is flat. So we can look at those things to get an idea of the genuses. And then further we will go into identifying species. And another thing that we do is if we get a sample, I have already told you we have these websites where they show the geochemistry, the biostratigraphy. So if we know the depth, there are some possible species at that depth. So if we have that possible species, it will be easier. We only have to look at those species to identify the species, whatever species we are looking through the microscope. So these are some things that we can do to make our life easier. Now here it is written geochemical analysis is size specific. Just like I told about the elephant and goat, a fat and thin guy eats different. So we have to separate it based on the size as well. See, so we have a seed. We will take this foraminifera and separate it based on the size. And anything, this is like 0.063 micrometer, then 150 micrometer, 250 micrometer, 350, 450, 500 micrometer seeds. So we get those size fractions. Anything below this 0.063 is not used for a geochemical, and anything above is not. Mostly in the papers that I have gone through, the ones that they use for geochemical analysis is from 250 to 350 and 350 to 450. So we only use those specific size ranges. Now we have picked these foraminifera and we are ready for the analysis. But we should only analyze the biogenic elements. I don't know if you guys are familiar with the term diagenesis. Diagenesis is something that happens after the death of the organism, right? So whatever trace elements, the lithium, magnesium, that was added into the calcite itself, the shell, whatever that happens after that, after the death of the organism, those are biogenic elements. So we have to remove that. Those are the contaminants. So that's why cleaning of the samples are important. So we cannot have a reliable data if we don't clean the samples. So these are the major contaminants that we see in coral and foraminifera samples. One is silicate, basically clay, and then iron manganese coatings, organic matter, exo contaminants from the lab. So the main important contaminant was the clay. Clay we know is aluminum silicates, and they have magnesium and these trace elements inside them. Okay, so if maybe you guys have studied like how smectite goes into the light and there is magnesium. Like I'm just giving an example of how clay can bias to our data. So removing the clay is an important step. So for clay removal step, what we do is we take the sample in these kind of Eppendorf vials. Then we no need to read this thing. I'm just showing this is a step. This is a procedure that we do. So we add milky water. This is deionized water, and we suspend. We ultrasonate. This is the ultrasonator, which suspends the foraminifera of the sample. So after suspending the sample, we will wait for it to settle down. So when it settles down, the sample will settle down and the clay will be in the suspension. So the basic idea is the difference in the density of the contaminants and the carbonate. This is the basic idea. So here it is a picture of cracking of foraminifera. So I was talking about foraminifera and corals. Corals are in powder form, but foraminifera is we have to break them before doing this clay removal. So this is that process. We use a syringe and microscope to do this. So I talked about water. We have to do this 3 times, and here we are using methanol. Methanol is even less denser than water, so it will be more effective in that suspension process. Repeat this 3 times, then again repeat this 3 times. So it will take almost 15 to 30 minutes for a coral sample to settle down. So it is a really time-taking process. So this is one clay removal step. For minimum, we have to do this 2 times. So that's why we are giving that much importance to the clay removal. If we don't, so look at this graph. We can see how the magnesium by calcium ratio was so high on the first unclean sample, and suddenly with the water step and the methanol steps, it suddenly decreased, and then it becomes constant. So when it becomes constant, that means that is the true magnesium by calcium ratio. These were because of the contaminants. And this graph is x-axis is aluminium, and this is magnesium. Aluminium is the basic component of clay. So this implies that more clay is there, more magnesium calcium ratios, magnesium or any other. Like I'm just giving magnesium as an example for the tracer and minor. So all those can increase because of the clay. Now the second contaminant that we see is the iron manganese coatings. So for iron manganese coatings we use reduction. I'm not going to these steps because I don't think there is any useful telling these things. Basically the reducing agent is hydrazine, and there is ammonium hydroxide and citric acid. We take it in a ratio, and this reducing mixture will be added into it. We will again ultrasonicate and centrifuge. Ultrasonicate means to make these things come into suspension. Centrifuge means we are settling things down in that pile, and we will take out the water and just the sample will be inside. Okay. Now this graph is actually showing us a problem that we face during the reduction step. This is the magnesium by calcium without reduction. This is the magnesium by calcium ratio with after doing the reducing step. So we can see all the points are on this side of the graph. So what it means is the magnesium by calcium ratio is decreasing when we are doing the reductive cleaning. But it is actually, if you see, I already told you this reduction method is used to remove the iron manganese layer, not the magnesium. So there is something wrong with this. So the problem is with the reduction is that it dissolves the carbonate. We don't want the carbonate to dissolve. We don't want the magnesium ratio to come down. So that is the problem with the reduction step. We don't do the reduction step in every sample. We only do it in the samples where this FeMn ratios, the FeMn contamination is too high. So we don't do this every time. Then another contaminant is organic matter. We do oxidation using hydrogen peroxide, and hydrogen peroxide will dissociate this organic compound into carbon dioxide and hydrogen. So basically it will be dissolved in the solution, so we can remove the organic matter that is there. and then the adsorbed contaminants will be removed using leaching step. Leaching step is again a huge big step where we are adding 1% ammonia in PQ, then 0.01 normal of nitric acid. So again, here is the actual leaching happening. The leaching is happening in this step where acid is removing the adsorbed molecules on the calcium. So in these graphs, you can see the big drop is happening during the clay removal step. All these graphs go down and they are flattened. So the clay removal step is where the most of the removal of contaminants is happening. So other steps are important, but the most important is clay removal. See, now still our sample is in solid form. The instruments that we have in our lab takes the liquid form samples. They take the samples and they make it into, they spray this liquid sample into the instrument. So we have to make it into the liquid state. So for that we do dissolution. We know carbonate dissolved in lower pH. So we use this HNO3, 2% HNO3 to do the dissolution. These are the main instruments that we had in that lab. So both are ICP instruments. ICP stands for integratively coupled plasma, and this instrument is OES, that is optical emission spectroscopy, and this is mass spectroscopy. So optical, I will give a small introduction on what is the main working principle of OES. They both have plasma basically. So what this plasma does in both instruments are different. In the optical emission spectroscopy, what it does is it excites the atoms, and when it comes down to its stable form, it emits like different characteristic wavelengths for different elements. So that is the working principle of OES, and for this they ionize the atoms, and every different elements will be having a unique charge to mass ratio, and based on the charge to mass ratio, we will be able to distinguish the elements. So this, so during my internship, I was seeing how these things work. There are some procedures on how we are feeding our sample into this. We have to create some standards, and there are some things that happens to the machine. Like after some time, the machine plasma will shift. There is some instrumental shift. How can we go about it? So what happens is that after some time, the measurement that they are getting will be changed because of some change in the machine itself. So we will take some standards. We know the concentrations of, and we will put that standards in between our samples. And every sample, those standards should show the same result. But since there is some difference that is happening to the instrument, they will show some different values. So what we do is we subtract that values from the samples to normalize the error that is happening.